the recording. Yeah, I know, but I wanted to show this because it looks prettier. Okay, so that's it. Wait 1 second. So let's start. In the last session, do you remember Friday? I mean, depending on what you did on Friday night, most probably you will not. But in our session, what we did was looking at two different ways to calculate the gain of an amplifier. Why an amplifier? Because the amplifiers are the building block for any kind of analog electronics. Whatever you do with electronics, you are always using an amplifier somewhere. If you are adding signals, you are integrating signals, differentiating. If you are making control or whatever, you are always using amplifiers there to keep the signal, the level of the signal at least to a given level with a given strength. Okay, so we saw two different ways to calculate the gain of an amplifier. The first way was, okay, that's the complex way. We get the long channel model, the full cut off, saturation, and linear region, and we calculate the whole transfer function, and then at the point of interest, and so this is gonna be the gain of the amplifier at this point. Okay, that's the complex way, and it's not very useful because it's quite a lot of work even for one single transistor. When you have 2, 3, 4, 10 transistors, that's impossible. Okay, it's too complex to do hand calculations. I mean, for computer simulation, you are using this, but for AC, but this is another question. And the second way we saw was, okay, let's do something more intelligent. First of all, let's use the long chart, the static model, the long signal model to calculate the quiescent point. And then we rewrite the circuit using the small signal model, and then we calculate the gain and so on. Okay? These are two different ways, and finally they are equivalent. But the second way, even if it looks a little bit more complex, it's much easier when you have more than one transistor. When you have one or more transistors. Okay, so it's always easier, and it's a two-step process. First, you calculate the quiescent point, and then when you have the quiescent point, you calculate the small signal parameters, and you replace all your transistors by the small signal model. Okay? Do you remember that? Yeah. Okay, you remember. I am happy. Any questions about that? No? Okay. But can you see any problem with this kind of thing? The problem is that this is only for low frequency. This is not valid for high frequency. For high frequency, there are a lot of other effects that will affect that are not reflected here with this simple model. So we have to go further into the physics of the devices, or at least into the description of the devices, to see what's happening here and how to put these other effects into our electrical model. Okay, so this is basically what we will see today, which is MOSFET capacitance models. How we add these capacitances to be able to use our models in high frequency, or at least medium frequency models. Okay, which is important. You're not only going to low frequency. Okay, yeah, questions? Okay, so go for it. First, we will see the intrinsic capacitances of the MOSFET model, then the extrinsic capacitances, the small signal model, the complete small signal model, including the capacitances and everything else. We will see how the full SPICE model is implemented. And then, as an example, we will see a common gate amplifier. Yeah, okay. So first of all, intrinsic gate capacitance. What does it mean, intrinsic? Intrinsic means that these capacitances are there, independently of what we do. They are always there, because they are built in into the system. They are for the operation of the device. Do you remember how the MOS was working? Yeah. No? So let me show you. So the MOS works simply by using these two regions, the source and the drain, and between these two regions we create a capacitor, okay, which is the gate and the substrate. And this works just by accumulating charge below the gate. Okay, so this is the channel, and in this channel we accumulate the charge. So by definition, our transistor is using a capacitor. So these capacitors, in fact, we have capacitors between gate and source, gate and drain, gate and bulk, drain and source and bulk, and so on. So all these capacitors are intrinsic. That means they are built into the system. So we are using them to make our system work. Okay, so we have to know how they are modeled or how they are included into the models in order to be able to use them. Okay? Yeah? Okay. So, moreover, apart from that, apart from this intrinsic, there are plenty of extrinsic capacitances, but this is another question that we will talk about later. Okay? Not now. And then, when talking about gate capacitance, which is probably the most important capacitance because it's the input capacitance usually, we have to distinguish between the three different regions we can have our transistor on. We can have our transistors in the triode, weak in the triode, or linear mode, or active saturation. Okay. We can even have the transistor in the subthreshold region, subthreshold or weak inversion. Okay, so we have these three different regions, and at each region, our capacitances will be different. Okay, so we have to know how these capacitances are modeled, or at least which is the value at each region. Okay, usually we will be working in the active in saturation region. Okay, so this is not a problem. Okay, any questions till now? No? Okay. So, first of all, let's see the transistor in saturation region. Okay, for the transistor in the saturation region, we have that the gate and the conductive channel are basically a parallel plate capacitor, okay, which is what we expect from the. Do you remember when kids they were talking to you about capacitor, about electrical field and capacitors and things like that? I think that was in electromagnetics. I think it was in first or second course. Maybe it was even Juanjo who told you about that. Do you remember? Yeah? Please tell me yes. Lie to me. Yeah, in the first year of so many years ago, at least 4 years ago. Oh, now you are grown ups. Anyway, so in this case, what we have is just a parallel plate capacitor, where all the capacitance we are seeing is the full capacitance. It's depending on the size, on the area of the gate, which is the width of the gate multiplied by the length, W by L, sorry, W by L, this is the area, okay, multiplied by the capacitance per area unit of the gate, which is the thickness of the outside, of the gate outside, divided, sorry, this is the dielectric constant, epsilon, divided by the dielectric thickness, TOTS. Okay? And we usually, this epsilon divided by T, we call it C prima, which is the gate capacitance per area unit. Okay? So this is more or less a constant capacitance. And okay, we can more or less approximate this capacitance using two lamped capacitors of 1/2 each. Okay, so one half goes to the gate to source, and the other one goes from the gate to the drain. Okay, and the capacitance from the channel to is nearly zero. Is negligible. It's not important. Okay, so instead of having the one single capacitor between the gate and the channel, we divide this gate to channel capacitor in two different capacitors. One that goes from gate to source, and the other one that goes from gate to drain. Okay? Doesn't it make you think about the things we saw in electrotechnia? The difference between the T and the pi model? Yeah, because they were equivalent. They were just two different ways to look at the same thing. In the one, we were getting only one capacitor, and in the other one, we were getting different capacitors. But as you see, engineering is always using the same ideas. We are recycling. Questions? No? Okay, now in the active region. Okay, in the active region, notice that there is a very interesting thing, which is that changing the VDS, the drain voltage, the current will not change. Okay? Yeah. Can you imagine that? So you are changing the VDS, the drain voltage, and the current is not changing. Okay, so that means that the VDS, that the voltage at drain, doesn't affect the charge into the channel. Okay, so using that, we know that the capacitance between the gate and the drain has to be zero in saturation region, neglecting obviously second order effects like the early effect, okay, or the output resistance. Okay, and then the other capacitance is the gate between the gate and the source. Okay, after doing some strange physical black magic, the idea is that we get that this capacitance is 2/3 of the maximum capacitance. Okay, just keep that in mind. Okay, and then the interesting thing in cutoff. What happens in cutoff when we have no channel? When we have no channel, we a capacitor. In fact, what the gate is seeing is a capacitor between the gate and the substrate, which is equivalent to the combination, as you can see in the picture, between the gate and the channel and the bulk. Okay, so this between the gate and the channel is equivalent to the COT, to the capacitance of the side. We already know that. And the other one depends on other things that we will see a little bit after. Okay. Yeah. But for large negative bias, what you get is that the gate channel is the maximum possible capacitance, which is UL multiplied by the gate capacitance per area unit. Okay, this is the maximum capacity, the maximum possible capacitance. So finally, what we get is this thing. This is the summary of all the intrinsic MOS capacitances. Okay, we have, sorry, we have this, at weak inversion, which is under the threshold. We get that the CGS is 0. CGS means between the gate and the source, 0. And between gate and drain, 0. Okay, we are below the threshold, so there is no influence whatever, because there is no channel here. So anyway, anything we do, the current is still 0. So there is no charge, no capacitances between these terminals. Between the gate and the bulk is this expression, which is the equivalent to 2 capacitors in series. Okay, so we get the minimum, sorry, of both of them. Sorry, the minimum. Okay, then we go to saturation. In saturation, we have that the gate capacitance is 2/3 of the CL side, it's the capacitance, and the other two are 0. Okay, this is because of the channel. And then in the linear region, the gate capacitance is equal to the capacitance between the gate and the drain, which is 1/2 of the mass. Okay? Yeah. So in fact, we will be probably using only the saturation capacitance. So you don't have to worry a lot about the rest. Okay, so these are the capacitances that are unavoidable because they are there just because the MOSFET is charge based. So the control is based on charge. So when we are having control based on charge, it's mandatory that we have these capacitances. Okay? Yeah, in fact, as always, I've been telling you lies. This is not true. This is only an approximation, just to show you something which is more real. Okay, these are the 3 capacitances of the I'm showing you here. In blue, this line is the gate source capacitance. The green one is the capacitance between gate and drain, and the red is the gate to bulk capacitance. Okay, as you can see, they are not constant. This is the weak inversion region below the threshold voltage. VGS is over VDS plus VT. Then we have this. We have it in the linear region. Okay. So as you can see, this is not constant, neither 0. Okay, but okay, more or less, yeah. Okay, this is engineering. We don't care about it being 2 or 0. That's 0. Okay, so in the cutoff, in the weak inversion, this is okay, more or less 0, and the other one, the red one, is okay. More or less, it is whatever it has to be. It's not a constant. It's not a constant, but okay, it's between 6 and 5. Okay, let's call it a constant. Yeah, okay. And then the other one, oh, yeah, this one is more constant. It's around more or less. Okay, it has a region where it is not a constant, but okay, who cares? Yeah, that's gonna be okay, 12, which is 2/3 of C outside. Okay, 2/3 of C outside means C outside is around 18 femtofarads. Okay, so if this is 2/3, if this is C outside, then CGS and CGD should be around 9, around 9 femtofarads. Okay, so this is okay. They are at 9, more or less at the end of the region, and they are changing between 12 and 9 and 2 and 9. But okay, let's call it a constant. Yeah, okay. This is because the transistors are quite small. Okay, not a modern technology. It's a 20 years old technology. But when you take into account that the MOSFET model is nearly 30, 40 years old, okay, you can understand that the approximations for that are not valid anymore. But okay, they are still giving you an idea of how it is working. Okay, so the actual working for CGS would be something like that, from 0 to here, constant, and then another constant here. Okay, that would be the idea, which is not exactly like that, but okay, it's not so far away. Okay, so you get the idea that this is an approximation. It will be false, but it will be a good approximation. Okay, questions? Do you have any questions? No? Okay. So now let's go for the extrinsic capacitances, which are the most important ones. Not the most important, but they will be always there also, because we are fabricating a physical device, and so when we are fabricating a physical device, everything is going to be there. So we cannot avoid, we cannot escape having physical elements. Okay, in this case, what we have here is, can you see that? Is that our gate has length, but has some small superposition between the gate and the drain. Okay, and also it has some overlap between and the source. Okay, so we will be having this direct overlap between the gate and the drain. Yeah, but also notice that here we have this. Okay, and this has a physical size that can be as 1 micron. Okay, so between this region and the drain and the source also, we have another capacitor. Okay, this is the capacitor in the fringe, in the borders. Okay, yeah. So we have these overlaps here, these two overlaps, and then we also have the junction capacitance. Okay, how does it work? The junction capacitance. Do you remember a diode? Do you remember how a diode works? More or less? Okay, let me try to share my screen. No, not share my screen, but okay, but this. Just to make you remember. Okay. Oops, I should. Oh. Okay, we have a diode, and then the diode is region is a PN diode is just a block of two semiconductors, one which is doped P and the other one which is doped N. Okay, do you remember that? Yeah, and here in the P doped diode, in the P doped region, we have an excess of P-type carriers, and in the other region, excess of N-type carriers. Yeah, do you remember? P-type carriers are holes, and N-type carriers are electrons. Okay, do you remember that? Yeah. Okay, remember that holes are not protons. Okay, holes are simply vacancies of electrons. Okay? Yeah. Okay, then let me do that a little bit bigger. In this region where you're having holes, 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 and electrons, okay, in this region, the electrons and the holes will tend to combine. Okay, and by combining, you are creating here a region, a depletion region, where the charge, the net charge, is 0. Okay? Yeah? So here you're creating, here you're having a different voltage, so you're creating here basically a voltage that is called the built-in voltage, which is related to the difference in doping of the system and so on. Okay, but the idea is that here you're having a given charge, two different charges. Okay, so the diode is governed by these two different charges, which is the same. I mean, they have to be electrically neutral. So you change the diode by changing these charges. So a diode, a junction, a PN junction, when it's in the cutoff region, is just a capacitor. Okay? Yeah? Yeah? Okay, so if we have other capacitors, wait 1 second, because it seems that I lost my camera. Okay. 1 second. And I'm sharing my camera. I cannot share my camera. Oh, I cannot share my camera. Wait 1 second. Let me stop it and enter again. Okay, 1 second. Okay, so can you see me again? Can you see my camera with the presentation below? Okay. Okay, sorry. Thanks. Okay, so now, so you understand now that here we are having the P-type region, which is the substrate, And we are having also the p-type, the n-type region, which are the and the drain. Okay, so between the source and the bulk and the drain and the bulk, we are having what amount to be basically two diodes. Okay, they are not exactly diodes, but they are simply junctions. So here we are having junction capacitances, which are equivalent to the capacitances of a diode. Okay? Yeah? Okay, hey, where is it? So, and these capacitances are modeled just by using this formula, which are the formulas of the capacitances of a diode. We will not derive them, just believe it. And the AD is the area of the device, of the drain in this case, and PD is the perimeter of the device. Okay? One of them, this first term is the direct capacitance, and the other term is just the fringe capacitance. So that depends on the perimeter. And this one, the first one depends on the area, and the second one depends on the perimeter, which is basically 2W multiplied by plus 2L, the perimeter, and the area is just W by L. This is for the normal case. When you are having concept cases, this gets more complex. Okay, notice that these two transistors are the same. Okay, this and this are exactly the same. Can you see it? No. Okay. Yeah, no, no, no. Okay, so let me show you. Okay, so we have this, which is a normal transistor. These small squares are the contacts between the metal that is going with the drain and the diffusion area, and these also are the contacts that connect the metal with the source to the diffusion area, to the contacts, to the N-type contacts. Okay? And this in red is the polysilicon. Okay? Yeah? Okay. So, there are times when these transistors are too long. Okay, you may have a transistor which is 1000 microns W by just 1 micron wide, 1 micron length. Okay, and so these transistors are very difficult to fabricate. In fact, they cannot fabricate it. So what we do is, instead of using one single transistor, we divide the transistor in two. Okay, so what we have is two different transistors. Okay, this is drain, drain. So drain, drain, and drain for the source. This is conceptual now. This is source, source. Okay, and then the gate is all this. Okay, do you see that? I just divided the transistor, one single transistor, in two different transistors. Okay? Yeah? And then what I do, or what we do, is just you getting this one and rotating just to here. Okay? So we get this like that. So what we get is two different transistors like that. And we overlap the sources because they are the same electrical node, so we can overlap them. Okay? And then the gate goes something like that. Okay? Yeah. So notice that in this case we are reducing the area of the total transistor, and then we are also reducing the capacitance at the source by 1/2, so, which is good. Okay? Now, do you understand that? Yeah. Everybody? Okay. So this is the basic idea of analog design. Once you layout design, once you get all the sizes, you have to define how to divide the transistors in the most efficient way. Okay, so this is what we see here. Okay, so in this case, we probably need to specify the areas and the perimeters for each one of the MOSFETs, because we can do things like that. Okay, so to make something which is quite long short, this is the summary of all the capacitances that we have at the MOSFET. Notice that here I'm already adding everything. In weak inversion, what we have for the gate and between the gate and the source and gate and drain is basically the overlap, which depends on the technology and how we are fabricating that. For CGB, the gate and the bulk in weak inversion, that means under the threshold, we get something that tends to COTS. And for the capacitance between the source and the bulk and the drain and the bulk, they are the capacitances for junctions. Okay, and then in the triode and saturation regions, okay, so we have all the other expressions. Okay, so but the idea is that the capacitances are not fixed. They are more or less fixed, but all these capacitances are changing. We approximate them by something more or less constant, but we have to know that this is false. Okay? So I'm giving you constants, but also I want you to remember that these constants are not true. Okay? So you just have to remember that this will change when you are actually fabricating the circuit or when you are simulating it. Okay, this is just for hand calculations and to get some idea on what is happening. Then, however, there is another reason that this is false. Why? Okay, this is false because we don't have this lamp, because these capacitances, the actual capacitance is the capacitance of a four-terminal device, not the capacitance, not four capacitances corresponding to a two-terminal device. Okay, can you see the difference? So we have some charges at the device, and these charges are depending on four different capacitors, four different voltages, just one, like in the case of a two-terminal device. So that means that our devices are our capacitances, our transcapacitances are much more complex than these approximations. Okay, but anyway, this is something that is dealt with in the simulation models and not in the so this is okay. Are curious about that, just go and study physics, and then you can go and look at the CVD's book, The MOS Transistor, or whatever book you wish, because it's a quite complex matter. Okay? Questions? Anybody has any question? No? Not yet? Okay, so let's see the MOSFET SPICE model. Do you remember making simulations with SPICE? Do you? More or less? You have never done simulations using SPICE? Now I'm very curious about that. Yeah, okay. Yeah. Only in CISE. Oh, then I have to tell you a little bit about philosophy. When you want to check if a system is working, how do you do that? How do you simulate an electronic system? If you want to simulate an FPGA, okay, you go and program the FPGA, and that's okay. But if you want to check if an analog circuit or a digital circuit, okay, an analog circuit is working, you use SPICE, okay? But what are you using in the other topics? What kind of programs are you using to simulate things? PSIM? Okay. But PSIM is just SPICE. It's just another brand of SPICE. SPICE, it's not PSpice or SPICE is another thing. Okay. So now I'm letting you homework, optional, obviously. But if you wish, just look what is SPICE. Okay, look at the Wikipedia and look for the antecessors of SPICE. How was called the antecessor of SPICE? The program that was before SPICE. Okay, and what does it mean, SPICE? Okay, so please try to do that. In fact, SPICE is a very powerful simulator in PhysE, and you have only used PSIM. You have not used. Okay, very good, Mark. Okay, but LabVIEW is not a simulator. LabVIEW is only to get the data. And what was before SPICE? Okay, anyway, you have used PSIM. No, not bias. Is the name of an astrological sign. Yeah, that's it. Cancer. And ER, do you know what it means? The two last letters? Means excluding radiation. And this is because it was developed in Berkeley during at the end of the 60s, and there was a lot of anti-militarism there. So they didn't want to simulate things related to nuclear bombs. It explicitly said that it was excluding radiation. So that's quite curious. And then they developed SPICE, which can do anything. Okay, anyway. You have not used LT SPICE? Neither? No? No? Okay. No. It's a little bit more powerful than PSIM, and it's free, and the simulator is better than PSIM, and and the good thing is that it's also free. But anyway, we will be using another simulator here. Anyway, when you wish to simulate a device, an element, you need to describe it using using a command. Are you familiar with that? Are you familiar on how you describe elements in SPICE? You just make a netlist, more or less. Okay. Okay, I thought. Okay, so let's assume that we have that in SPICE we have this. Okay, R1, R2, VI. Okay. Yep. So the first thing in SPICE is assigning nodes. This is ground, so this is node 0, node 1, and node 2. Okay, so in SPICE, we would do something like that. Netlist, starting with a star, and then we say R1 between 1 and 2 with a value of, let's say, 1 key. R2 between 2 and 0, let's say 2 keys. And then V1 between first the positive 1 and 0, let's say 2 volts. And then this is the netlist. We are just telling the simulator that the device, that what is each element, just by describing. This is in fact a net. Okay, you're describing just the topology of the circuit by describing the nodes. Okay, and then we give it, for instance, the analysis DC of V1 between 0 and 5 volts with 0.1 volts step. Okay, do you remember that? Yeah. Okay, it's very easy. The idea of a SPICE is that it had to be very easy because it was destined to engineers. Okay, so it couldn't be anything complex. Okay, just joking. So, but the idea is that all the elements are defined in this way. First, you need a name where the first letter defines the kind of device, the kind of element. Okay, M, MOSFET, resistor, capacitor, inductor, Q for bipolar, and many other different things. Okay, then just after that, without a space, a label, which is identify the element. Okay, and then the topological description, nodes. It can be 1, 2, 3, whatever you need. And then other things that are the parameters. Okay, and then in these parameters, for instance, resistance, you are saying that it is 1 kilo ohm resistor, but you can also give it, for instance, the temperature coefficient dependence. Okay, or more things. Okay, it depends on how the mathematical model is describing the behavior of this element. Okay? Yeah. So, for the MOS transistor, we are having the most basic thing, which is the M plus the label plus the nodes in this order, drain, gate, and source. Notice that by construction, the drain and the source are symmetrical. You can swap them without any problem. Okay? Drain and source can be swapped. When you have the drain, you can put the source and vice versa, and the model will behave exactly the same because the physical device is symmetrical in drain and source. Not on the other things. Okay, but on drain and source, it has to be symmetrical. Then you have another different node for the bulk, and then you have another thing which is the model name. The model name, you have to define if it's an NMOS, PMOS, or other things. And then you define the parameters of the transistor, which are the width and the length. Okay, and then other things that are optional. If you don't give them to the simulator, they are calculated automatically, like the area of the drain, the area of the source, the perimeter of the drain, the source, and all the more complex things. Okay? And so this is what you are providing to the simulator. This is more because otherwise, if you have to debug your netlist, it can be complex. Knowing the format is always interesting. Okay? Yeah, but anyway, the good thing also about models is that we have plenty of models, of MOSFET models to simulate. In fact, every 4 or 5 years, we have a different standard model. Now the standard model is something which is called PSP11, which stands for Penn State Model Simulator, and it's also a mixture with something that they developed at the EPFL in Lausanne, in Switzerland, which is a mixture of two different models that are more or less behaving similarly. But okay, never mind. However, the most known model is what is called BSIM, which stands for Berkeley Simulator. Okay. At the University of Berkeley, and the creator, Liu, is one of the few device engineers that has got a millionaire just selling his expertise on how to implement the model. So it's quite interesting. With this model, okay, it's a very good model, which is continuous and has many different good things, but it has something like 300 different parameters. Okay, 300 different parameters is quite a lot. So it's a complex model to work with, but it's also a quite great model. So it's probably the most important thing. And you see here that we are using all the different things we have been discussing about these days. We have discussing about the thickness of the gate oxide, the initial threshold voltage, the mobility, the different resistances, the saturation voltage, some different gate capacitances, some different effects on the length, some effects on the threshold voltage. Do you remember that the threshold voltage was changing with the VDS? So here we are having these parameters, plus parameters defining the mobility, noise, the junctions, plus temperature effects, and many different things. So up to 300 or more than 300. Okay, so it's quite a bad model to work with in this case. For parameter extraction, it's quite a nightmare. Okay, but in general, the idea of the MOSFET model is very easy. It's just this thing. Okay, then how they say the devil is in the details. The details are how to model these parasitic source, these sources, how these controlled sources are done. But all the other things, as you can see, are more or less straightforward. They are diodes, which are usually in reverse between the source and the bulk, and the gate, and the drain and the bulk. Junctions. We have also some capacitances here, and also capacitances between the gate and everything else. And here we have the gate capacitance, and the most important thing, what we have always used, is the ID, which is the current. Okay? Yeah, everything else are just a mixture between intrinsic and extrinsic parasitic devices that are there by construction. Okay, so the MOS device is quite a complex thing to simulate. Okay, and then this is for an N transistor. For a P transistor, things are slightly more complex, and we have another capacitance which is related to the capacitance between the well and the bulk. This is just another capacitance. Okay, and then for the small signal model, we just replace the current by the transistor, by our small signal elements, and we get complex device. Remember that we have this output, we already know it. This is the bulk transconductance, and this is the GM, okay, the normal transconductance. What you always used were this, the output resistance, and most probably also this capacitance. All the other things is new to you, I think. Okay, so, but this is the most complete, small signal model that we will use for hand calculations. Any questions till now? No? Okay, let me see, what is it? Okay, any questions? Let me see. Yes or no? No questions. Okay. Then, when you want to do, when you want to use this simulation model in SPICE, you can do something which is a mixture between hand calculations and the SPICE simulations. What you can do is asking for the computer to return you the operation point, the quiescent point. And then you can use this quiescent point to get the small signal parameters and do your hand calculations. Okay? This is something that you can do. Anyway, in any case, usually you can also get the final result by just doing that. But it's an intermediate step that you can use to provide you the different parameters you need to perform your hand calculations and get the correct dimensions for your system to work correctly. Okay, so when you ask for the operation point for the .op, the SPICE will return you everything you need, not only to get the quiescent point, but you also get, or you can get, all the different things for the small signal model. Okay, this is important when you want to debug your circuit. Okay, so, and with that, I think we will end this session today because it's already. Oh, okay. Let's see. I don't know if we will end, but we have a little bit of time. Let's just check the common gate amplifier. Okay, do you remember the common gate amplifier? Yeah, is this a little bit? Okay, so you have the slides, but I'll do the hand calculations because I think it's a little bit better. Okay, so what is the common gate? The common gate, let me redraw the system. Wait 1 second. So the original system is this, okay? But this is probably a little bit complex to follow. Another way to draw that, okay, let me first of all draw it here. Okay, so this is, we have here two resistors which are just this is a current source, which is just biasing the transistor. Here we have the output with a given load. And the input is at the source. Okay? Yeah. This is called common gate because the gate in AC connected to 0. In AC, this is a short, so the gate is at 0. This is why it's called common gate. Okay, so we can get all the different things here. VT is 1/2, beta is 1 milliamp over volt squared. I'm writing too fast for this. Shit. Okay. Easily is quite easy to draw it. Okay, we know that the threshold voltage is 0.5 volts, beta 1 milliamp over voltage squared, lambda 0.01 volts to the -1, gamma 0.36 volts to 1/2. This gamma and the flat band voltage, these two are related to the threshold voltage variation. So they will provide us with the bulk transconductance. Okay? And then we have other things like BCC, which is 3.3, and R1, and the bias current, which is 300 microamps, and the load, which are 10 kilo ohms. Okay, so first of all, they tell us that we need that the output at the quiescent point has to be 1.75 volts. Okay, and how much is R2? So, I think that you can calculate that by yourselves. But this is equivalent to having VGS equal to 1 volt. This is for home, if you wish to do some calculation. And then this implies that R2 are 100 Ks. Okay? And then with that, we calculate transconductance, which is Gn as the square root of 2 beta by the bias current at the quiescent point, which is 0.5 milliamps per volt. R0 is equal 1 over lambda multiplied by the current at the quiescent point, which is in this case 800 keys. And the bulk transconductance using these parameters and the other ones is gamma G over minus PB S. In this case, BS, this is the source, and the bulk is connected to ground always, and in the quiescent point, VI is 0, so the source and the bulk are at the same voltage, so this is 0. Okay, so this is 0.23 milliamps per volt. Okay. Any questions? I'm just giving you the results. Yep. Okay. Now let's go for the small signal analysis. Okay. So for the small signal analysis, we first replace all the sources by sources with 0 value, plus all the capacitors by short circuits, and so on. Okay, so what we get is something like that. Okay, this is input, which is connected to the source of the transistor, and here this is RL, and the gate is connected to ground, and the bulk, okay, in this case we are connecting it also to the source. Okay, the gate is connected to ground just because it was connected with a capacitor, and this capacitor in AC is just a short circuit, so this goes directly to 0. The current source that was in here just goes to value 0, so we forget about it. Okay, so we just get this. Okay, we go to the small signal model now. We just replace the transistor by its small signal model, and we get something like that. This is the input, and the input is connected. First, it is connected. Let me change the color. First, if it is to the output resistance. Okay, then it is also if this is the drain, and the current flows in this sense with something which is Gn multiplied by VGS. Okay, and then we also have the bulk transconductance, which is GMB multiplied by VBS. And here we have, okay, this is already the outside. This is the output, the load resistance, RL. Okay, can you see that? Now we know that the input is minus VGS. VG is 0 and VS is VI. So VGS okay, and then this is also equal to minus VBS. So this goes to ground, not to here. Okay, this is ground. This is not connected here. There is no connection here. Okay. So by replacing that here, it's obvious to see that the output is just GM plus GMB multiplied by RL by VI, when R0 is much bigger than the output. Okay? Yeah. And for our case, this is 7.3. Any questions? Any questions till now? No? No questions. No news, good news. Okay. So now we have the small signal model. Okay, this is 3. Okay, so let's go for the important thing, which is the high frequency analysis. Okay, so let's do things easy. Let's define this GM plus G and B just to keep things simpler. And the capacitance at the input is just capacitance between the gate and the source plus the capacitance between the gate and the bulk. Okay? And at the output, we have the capacitance between the gate and the drain plus the capacitance between the drain and the bulk. Okay? And then using that and replacing, including our capacitances, we have that this is the input the output and the model has this gate capacitance, so this input capacitance, this output resistance, plus this output capacitance plus the current source, which is Gm prime by VGS. Okay? Yeah? Everything here, everything I'm telling you is in the slides. But when you have formulas, I think it's much better to develop them one by one than just giving the slides, because otherwise sometimes it's complex. Okay, in this case, if we neglect this current, which is always the easiest way to do, the voltage at the output is just the voltage, the current flowing through this impedance. Okay? So the output, in this case, is going to be Gm prime multiplied by the output resistance over 1 plus C output okay, it's just the voltage is just the current multiplied by the output, so it doesn't make any, it's not complex. Okay, so from this the gain is just this Gm prime over, okay, multiplied by RL plus the frequency, the output capacitance, and the load resistance. Okay, so in this case, notice that the pole, so do you remember? Have you ever done both diagrams? Do you remember both diagrams? Okay, so the pole here, this is more or less here, and here this is going to be given by this frequency. Okay? In fact, by this divided by this. But the important thing is that the output is what is defining the output of the system. Okay, which is defined by these capacitances. Okay. Any questions? No? You don't have any kind of question? So my proposal is that we adjourn the session till Friday, because it has been most probably a hard session. Okay. Yeah, let me stop the recording.